Now that we have a decent idea of what curvature means, let's look at working with curvature. The linear curve, which is a straight line, has a curvature that's equal to 0. Let's see how we get that result. If I have a vector valued function given by the components a times t plus x naught, b times t plus y naught, and c times t plus z naught. If I take the derivative with respect to t of these components, I get r prime of t is equal to the vector components a, b, and c. The unit tangent vector for this curve is given by r prime over the magnitude of r prime. The magnitude of r prime is the square root of a squared plus b squared plus c squared, and the vector components are given by a, b, c. I have to take the derivative of the unit tangent vector to determine what the curvature is. So the derivative with respect to t of the unit tangent vector gives me the 0 vector, or the components 0, 0, 0. My curvature, kappa of t, is given by 1 over the square root of a squared plus b squared plus c squared times the derivative with respect to t of capital T, which in this case is just 0, and this gives me a curvature of 0. In the case of a circle, my curvature will be constant, and let's see how that turns out. If I have a vector valued function, r of t, that's given by the components capital R times cosine t and capital R times sine t, where capital R is a constant of some sort, my first derivative of my vector valued function is given by the components negative capital R sine t and capital R cosine t. The unit tangent vector will be given by 1 over capital R times the components negative capital R sine t and capital R cosine t. This reduces to the components negative sine t and cosine t. The derivative of the unit tangent vector with respect to t is given by the vector components negative cosine t, negative sine t. Kappa of t is given by 1 over r times the square root of cosine squared t plus sine squared t. This just gives me 1 over capital R. This is a constant, and my curvature for this circle is constant. Now there is an alternative curvature formula. If we apply what we know about properties of vector valued functions, we can develop an alternative formula for curvature that can be useful for working with trajectories of moving objects, especially in 3D. We'll let the vector r be the position of an object moving on a smooth curve. The curvature at a point on the curve is given by kappa is equal to the magnitude of the cross product of the velocity crossed with the acceleration divided by the magnitude of the velocity cubed. This is where the velocity of the object v is equal to r prime, and the acceleration of the object a is given by v prime. Let's use this alternative formula for curvature to find the curvature of the parameterized curve described by the vector r of t is equal to the components 4t, 3 sine t, and 3 cosine t. The alternative curvature formula is written as kappa is equal to the magnitude of v cross a over the magnitude of v cubed. V of t is given by r prime of t, and that just gives me the components 4, 3 cosine t, and negative 3 sine t. The magnitude of the velocity is 5. The acceleration is given by v prime of t, which is equal to 0, negative 3 sine t, and negative 3 cosine t. The cross product of the velocity and the acceleration, v cross a, is given by the determinant of a 3 by 3 matrix. I hat, j hat, k hat in the first row, 4, 3 cosine t, and negative 3 sine t in the second row, and 0, negative 3 sine t, and negative 3 cosine t in the third row. I break this up by expanding about the first row. This gives me a vector with the components negative 9, 12 cosine t, and negative 12 sine t. The magnitude of the cross product is 15, so that my curvature using the alternative form is given by 15 over 125, which reduces to 3 over 25. And this is the measure of how tight my curve is. Here's another example. I want to use the alternative curvature formula to find the curvature of the parameterized curve described by the vector r of t is equal to the components e to the t cosine t, e to the t sine t, and e to the t. Again, my formula for curvature is given by the magnitude of the cross product of the velocity with the acceleration over the magnitude of the velocity cubed. The velocity has the components e to the t times the quantity cosine t minus sine t, and e to the t times the quantity cosine t plus sine t, and e to the t. The magnitude of the velocity is given by the square root of 3 times e to the t. My acceleration is the first derivative of velocity with respect to time. This gives me a vector with the components negative 2 e to the t sine t, 2 e to the t cosine t, and e to the t. I compute my cross product using the determinant of a 3 by 3 matrix, and I get a vector with the components e to the 2t times the quantity cosine t minus sine t, e to the 2t times the quantity cosine t plus sine t, and negative 2 e to the 2t. The magnitude of my cross product gives me square root of 6 times e to the 2t. My curvature is given by square root of 6 times e to the 2t over 3 square root of 3 e to the 3t. This reduces to the square root of 2 over 3 e to the t. Now you get to try it. Pause the video and use the alternative curvature formula to find the curvature for the parameterized curve described by the vector r of t with the components square root of 3 sine t, and 2 cosine t. When you are ready, restart the video to check your understanding. We want to use the alternative curvature formula that's given by kappa is equal to the magnitude of the cross product of the velocity and the acceleration over the magnitude of the velocity cubed. The velocity has the components square root of 3 cosine t, and negative 2 sine t. The magnitude of the velocity is 2. The acceleration has the components negative square root of 3 sine t, negative sine t, and negative 2 cosine t. I set up the cross product using the determinant of a 3 by 3 matrix, and I get a vector with the components negative 2 square root of 3, and 0. The magnitude of my cross product is 4. The curvature is given by 4 divided by 8, or 1/2. This is how I can work with curvature using an alternative formula. Let me know if you have any questions.